Hello everyone, and today we're going to have a look at work and power. So we've come out of looking at various different equations about motion, and that has led us into force and acceleration. So we should now have a clear idea of those concepts. So now we need to tie in what is the idea of physical work. So when you think of the word work, you might think of some chore that needs doing, some kind of housework or homework or other task. But work is also a way to quantify how productive a force is. So we can precisely calculate the amount of work, and we can relate it to a precise amount of energy as well. And this is where physics starts to get very, very abstract, but also incredibly useful for all manner of things. So, what is work done, and how do we calculate it? Well, it's the force applied multiplied times a distance it is applied over. So, in other words, work done equals force times distance. So what would you say is the unit of work going to be? Well, technically, it is the Newton meter, and we can see that force is measured in newtons and distance is measured in meters, so when you multiply them together, getting the Newton meter makes sense. However, we did just say before, work done is also connected with energy. So what does that mean the unit of work done could also be? So let's look at that equation again. To calculate work, you want to use W equals FD, where W equals work done, which we can measure in, as we said, Newton meters, or what else? The unit of energy, which is the joule. F is, of course, the force applied in its unit of newtons, and D is the distance moved in meters. So that's how we would symbolize and represent that equation. So this shows a direct connection between physical work done and an amount of energy used in joules. And joules is the universal unit of energy of all types. So being able to relate something to joules means we can easily relate it to any other kind of energy. So let's do a short example here. During the ascent phase of a bench press, the lifter exerts an average vertical force of 1200 newtons against a barbell, while the barbell moves 0.6 meters upwards. So that guy there is pushing the barbell upwards. How much work did he do to the barbell? Just have a moment to think about that. Pause the video if you would like. But I can tell you that, seeing as work equals force times distance, that means the force 1200 newtons multiplied by the distance 0.6 meters means the lifter did 720 joules of work on the barbell. So let's have a look at another work equation, shall we? W equals Fs. So this looks very similar. In fact, in this case, the only difference is we're using displacement in meters. Now, this might seem to be an insignificant difference, but don't be fooled, because displacement, remember, is a vector, and sometimes it actually matters in which direction your force is heading. And this leads us on to talking about positive and negative work. What do we mean by positive and negative work? Well, positive work is done when the direction of the force is the same as the direction of the motion of the object. For example, the ascent phase of the bench press, when you push the bar upwards, throwing a ball, you push the ball away from you, and the push off of a jump when you push yourself away from the floor, for example. On the other hand, negative work is done when the direction of the force opposes the direction of motion. So during the descent of a bench press, you are still pushing up on the bar, but the bar is moving downwards. And you know you are pushing up on the bar because if you weren't, that big heavy bar would fall on your head. Catching a ball is also opposing the motion, so the force of your hands is pushing into the ball to slow it down. And the landing phase of a jump. So when you land, your legs bend, but they are actually still pushing upwards to stop your body from crashing into the floor. So these are all examples of negative work. So remember, in both cases, the work is being done on the same object. In other words, it's being done on the bar, on the ball, or on your body. Work done is positive or negative relative to the object it is being done on. So as an example of that, let's think about catching the ball. When you catch a ball, your hands do negative work on the ball to slow it down. But it's also true that the ball does positive work on your hands, and that's why you feel the ball slap into your hand when you catch it. That is the positive work that the ball is doing into your hand. So it's important to make sure you're thinking about the right object when you think about whether work is positive or negative. So let's look at a different example of calculating work, shall we? So in this case, during the descent phase, when the bar is moving downwards, the lifter pushes an average vertical force of 1000 newtons against the barbell, while the barbell moves 0.5 meters downward. How much work did the lifter do to the barbell? So try and work it out. Be careful about which way the forces are going. In fact, work is force times distance, which means it's 1000 newtons pushing upwards times minus 0.5 meters moving downwards. So you have 1000 times minus 0.5. So the lifter does negative 500 joules of work in this case. It's also possible, of course, to do zero work. You might have noticed that in order for work to be done, something has to happen. And in terms of mechanics, when we're dealing with moving objects, we judge this by distance, by how far the object has actually moved. So what about this guy? This guy is pushing as hard as he can against this wall, but the wall doesn't seem to go anywhere. So he's using a lot of effort, but he isn't actually doing any work. His force is not being productive. He is, in fact, just wasting his energy. So here's a question. How would you calculate the work done in walking up a set of stairs? So try and think about everything you've learned about physics so far, and you might be able to come up with a process. So if you were climbing a set of stairs like this one, you would first need to consider the work equation, obviously. And for that you need the force. Well, the force is going to be based on your weight. So let's say you weigh 65 kilograms. That means your downward force is going to be 65 kilograms times 9.8 meters per second squared, your acceleration due to gravity. That means your downward force is 637 newtons, which is the amount of force you're going to have to lift up in order to raise your body up the stairs. So what is the displacement? Well, the total displacement is going to be the height of each step. Let's say it is about 20 centimeters per step. That's 0.2 meters. So the work done per step is going to be 637 newtons times 0.2 meters. In other words, 127.4 newton meters. Or you could say that that is in joules, and then you just need to multiply that by the number of steps you are walking up. Now, strictly speaking, of course, there is a small amount of horizontal movement as well in walking up a set of stairs, and we haven't taken account of that, but you can see how we would calculate the amount of work done in climbing the height of this set of stairs. Let's sum up here, shall we? What is work again? Well, work is a precise measure of the productivity of a force or some other effect. In the way we have defined it, it's the productivity of a mechanical force, the force applied times the distance it's applied over. But as we said, work is also a measure of energy, so it's possible for work to be done in different ways. Our final topic is that of power. Just like speed is the rate of increasing distance, power is the rate of work being done. So something with more power can do more work faster. And this all makes intuitive sense, but we can put specific values on this as well. So what do you think the equation for power is going to be? Have a think about that, and on the next slide I'll tell you. So the power equation works out as follows. If work is force times distance and power is the rate of doing work, well, you may remember a rate is how much of something happens over time. Power then is work divided by time. But we can use this as an example of seeing how things can change into other quantities in physics. Power, incidentally, the unit of power is joules per second, or watts. Power can be work over time, but if we remember that work equals force times distance, that means it's Fd over t. But there's only multiply and divide there, so it really doesn't matter what order we do that in. So we can equally write it as F times d over t. D over t, you might remember, is velocity. So power is also force times velocity. So let's finish off with one final example. During the lift of a bench press, two lifters each exert a different force on the barbell while it moves 0.8 meters upwards in a given time. And there you see lifter A gives a force of 1000 newtons for 0.5 seconds. Lifter B gives a force of 1100 newtons for 0.75 seconds. So which of these two lifters has the greater power? Well, let's work it through. For lifter A, the work done is the force times distance. That's 1000 times 0.8 meters. That's 800 joules of work. And the power of that work is the 800 joules divided by 0.5 seconds that it took to do it. That's 1600 watts. For lifter B, we can see that he's actually not quite as powerful. The force times distance, 1100 times 0.8 meters, means that 880 joules of work were done. However, it took longer to do it. So when we take the power equation, the 880 divided by 0.75 means the second lifter only had a power of just under 1200 watts. So lifter A has the greater power, even though the amount of force he's putting out in total is actually smaller. And that's all we're going to go through on work and power. That's all from me for today. I'll see you next time.